Welcome to Physics 371 Online. Today I get to tell you about a method for solving for the electric potential that's really cool. It can be used in problems especially involving charges and conductors. This classic problem illustrates the method. It contains a point charge Q sitting a distance d above an infinite grounded conductor. And when it's grounded, then the conductor has a potential equal to 0. So the question is, what is the electric potential in the region above the infinite grounded conductor, which is where the point charge Q is sitting? Knowing the answer to this will allow us to figure out what the force is between the point charge and the conducting plate. And of course it's clear there will be a force because this point charge will attract a negative charge, a charge opposite to its own charge, near the center of the conductor, and that will produce an attractive force. Now it's clear that this is a tough problem because the charge Q, which I'm assuming is positive for the purpose of discussion, induces that surface charge, and those charges move around. So we don't have a static charge distribution here, we've got one that's dynamic. So how can we proceed to find the potential? Well, let's review the mathematical problem first. First, we have to solve for Poisson's equation subject to certain boundary conditions. So we're trying to find the potential V that satisfies this equation where V is equal to 0 on the surface of the grounded conducting plate at Z equals 0, and V has to go to 0 when the distance away from the plate becomes large. So in other words, for a point x, y, z tending toward infinity, the electric potential should go to 0 for that solution. And one of the things about this method is it relies crucially on a corollary to the first uniqueness theorem that we talked about in class. The corollary to the first uniqueness theorem tells us that these boundary conditions, along with knowing the location of the point charge, determines a unique solution to the potential in this region above the plate. So here's the original problem. And what we're going to try to do is try to guess the solution to this problem using a trick. So what's the trick? The trick is to create an auxiliary problem which has the same charge density above the plate and satisfies the same boundary conditions, but that contains no conducting plate, because it's the charge on the conducting plate that makes this problem difficult to solve. So here's the idea. We replace the original problem with an auxiliary problem that still contains the original point charge, but now removes the conductor and instead introduces a negative Q charge the same distance below the origin that the original charge was above it. Notice that every point in the z equals 0 plane where the grounded conductor used to be will now be exactly the same distance away from the positive and the negative charges. And therefore the potential at any point in the z equals 0 plane will be 0, because that point will be equidistant from two opposite point charges. That's the genius of creating this auxiliary problem, because now we satisfy the same boundary condition where the conductor was, but the conductor's not in the problem anymore. The auxiliary problem therefore has the same charge density above the plate, above z equals 0, and it has the same boundary condition of v equals 0 in that plane, and of course v still goes to 0 when we get really, really far away. For large values of z, then these two point charges look basically like neutral charge, which means the potential will go to 0. And according to the corollary of the uniqueness theorem, this means having the same charge density in the region above the plate and satisfying the same boundary conditions. That means that these two problems have the same solution above the plate, and it tells us the solution is unique. Note, One thing that is different about the problems is that the auxiliary problem has introduced a negative charge below the plate. So they have different charge densities. The original problem and the auxiliary problem have different charge densities below the plate, but that's not the region that we're interested in. We only care about the solution for V above the plate. So therefore, we don't have to worry about this negative charge spoiling the solution. So imagining that we have a general point with coordinates x, y, and z, it's very easy to write down the solution for the potential at that point because we simply have 2 point charges. And we can easily write down what the distance is between the point x, y, z and the 2 point charges just using the distance formula. As a result, our electric potential solution will have the sum of 2 terms. One for the positive charge on the positive z-axis. So that's 1 over 4 pi epsilon 0 times q over the distance between that charge and the point in question. And that'll be x squared plus y squared plus z minus d, quantity squared. Of course, just notice now there should be a square root there because the electric potential expression is for charge divided by distance. So that term in the denominator should have a square root. And then the second term minus q, because that's the negative charge below here, divided by its distance from the general point x, y, z. And the only difference in the denominator is now it will contain the term z plus d, quantity squared. And of course, that should also have a square root. Notice that this solution clearly satisfies the stated boundary conditions. If we look at z equals 0, we see the 2 terms are equal and opposite, and so the potential goes to 0. And when x squared plus y squared plus z squared becomes large, then the potential indeed goes to 0. The idea in the image method, again, just summarizing the basic approach, the idea is to construct an auxiliary problem by removing the conductor and adding an opposite charge, which is called the image charge, at just the right place to satisfy the V equals 0 condition at the grounded conductor surface. And if we can do that, then we can rely on the uniqueness theorem to change the original problem into a much more easily solved problem. Having the potential V of x, y, and z in the region that we're interested in also allows us to calculate right away the force between the point charge and the plate. Also, it allows us to calculate the surface charge density sigma on the plate, and knowing sigma, we can then calculate the total induced surface charge q on the plate. The details for these calculations are in the text, so make sure that you see the text and look through the examples. We'll also talk about some of those in class. I'll see you there.